Hello everyone and welcome to this session where we will use the program Ftool to perform structural analysis for the beam shown on screen. The beam has a total length of 48 feet, consisting of two spans that are equal in length. There is a 20 kips concentrated load acting mid-span between A and B, while the second span BC has nothing acting on it. The support at A is a pin, while supports at B and C are rollers. It is given to us in the question that support B settles by 1.5 inches. This means that there will be a vertical displacement at point B directed downwards. Also given to us in the question are the modulus of elasticity, which is 29 times 10 to the 3 ksi, and the modulus of elasticity of the beam, which is 750 inches to the 4. Once we are done with our structural analysis for the beam shown on screen, we will ask the program Ftool to draw the shear force and bending moment diagrams as well as the deflected shape of the beam. As I mentioned in the previous session, I strongly advise you to solve such beams by hand first, and then you can use a computer software to verify your solution and to acquire computer skill. The solution shown on screen is obtained using Maxwell's method of consistent deformation and using the conjugate beam method by selecting RB as our redundant. Of course, here the selection of the redundant is not arbitrary because of the specified displacement at point B. Therefore, you have to choose RB as your redundant in order to obtain the hand-made solution. Let's say that you have done that and that you've calculated your redundant RB. Then using RB and on the actual structure, you can find the rest of the reactions using statics, and then you can draw the shear force and bending moment diagram. Let's say you did all that by hand and now you want to check your solution by performing structural analysis for the same beam but using the program Ftool. I have already double-clicked on the icon of Ftool to have it initiated. I'm going to go to File, Sign Convention. Bear with me, I have two screens opened. And add a tick to plot diagram values on the compression side of the member to be consistent with the textbooks that we are using. Then I'm going to do what I did in the previous session. I'm going to go to Options, set these three items here to large so that the text will be clearly visible. Then I'm going to go to Units and Number Formatting, and I will select the United States customer units as my units for the current example. Click OK. What you can do at this particular point in time is you can go to File and save this file as a template. For example, you can call it US template. This way, whenever you have a problem that is using the United States customer units, you can open this US template, which is actually empty, and start entering all the information that you want. You can do the same thing for another template and call it metric template, but that template would be for problems that use the metric system, kilonewton meters, and so on. Next, I want to add the nodes of my beam, so I'm going to click on keyboard mode, then node, and here I'm going to add the first node at 0, 0, the second node at 12 feet, the third node at 24 feet, and the last node at 48 feet. I can click on Fit World on screen. Then I'm going to remove the keyboard and use the Insert Member button to connect my beam segments to each other. You can actually use this tool here, which is Insert Dimensions, to actually show the dimensions of the spans that you have drew. And at any particular point in time, if you don't really need these dimension lines, then you can just select them and click on delete. The next step is we're going to define the material that will be used for this beam. Remember, I told you in the data insertion area here, you need to first define the entity and then you can insert the properties in it. So I'm going to call this material 1. I'm going to click done, and here I'm going to add the value for the modulus of elasticity, which was given as 29 times 10 to the power 3. So here I'm going to insert 29 e to the power 3. I'm going to select everything on screen, and I'm going to tell the program Ftool assign this material to the selected beams through this button here. Next, I will go to the section properties. Again, I have to define a section first, so I'm going to name it section 1. We don't have axial deformations here in this beam, as the rollers permit the displacements in the x direction, but if in any case you want to prevent axial deformations, you can just add here a very large number. But in this particular problem, whatever value you insert here is not actually going to interfere with our solution, and here we're going to add the value that is given to us in the question, which is 750. So I'm going to insert here as 750 inches to the power 4. Again, I'm going to select everything here, and I'm going to ask the program to assign this section to all the beam segments shown on screen. The third step is to add the supports. The first support here is a pin, so I'm going to prevent the displacement in the X and in the Y, but allow the rotation around the Z axis. And this setup here, I'm going to assign it to this node through this button. Next, we're going to be having a roller. The rollers are going to be at this point and this point. Let's define this point first, and you will see why in a minute. I'm going to say that I have a roller here. This roller prevents the displacement in the y direction, but allows displacement in the x and allows the rotation. So I'm just gonna fix the displacement in the y direction here and ask the program to assign this setup to this particular node. This is a roller. Now, in terms of the intermediate roller here at B, I'm going to use the same setup shown here for the degrees of freedom. The roller actually prevents the displacement in the y, but allows the displacement in the x and the rotation in the z. And on top of that, I'm going to add a prescribed displacement, which was given to me here in the question. It was stated that support B settles by 1.5 inches. So I'm going to go here and tell the program Ftool that I do have a roller at support B, but this roller is going to sink downwards by 1.5 inches, which is known here as a prescribed displacement. So I'm going to add 1.5 inches with a minus sign to indicate that this movement is actually directed downwards. Then I'm going to assign this entire setup now to this particular node by clicking on this button here. You can see that this roller has no specified displacements, but this roller has a specified displacement by 1.5 inches. Now we are ready to insert our loads. So I'm going to go here to concentrated loads. Again, you will have to define your load first, give it a name. So I'm going to call it load 1 and insert the value given to us in the question. You can see that at this particular point here we have a concentrated load of 20 kips. So here we will be having 20 kips directed downwards. So it's going to be minus 20 kips, and I'm going to assign this value to this particular node here by clicking on this button. The setup is now ready. If you click on any of the output diagrams, the program will ask you to save the file first. Again, in this particular problem, we don't have any axial forces, so the axial force diagram will show nothing, but we can use it to display our reactions. There you have it. These are the reactions. Next, we can remove the reactions and draw the shear force diagram. and our bending moment diagram. If we compare these values to these shown here, we can see, can click on this one here and bring that back. You can see that the values are actually the same. If you want the same level of decimal digits, then you can come here and ask the program to show you more decimal digits in terms of the forces and the moments. Click OK, bring back the figure, and then you can compare. This here is your bending moment diagram, and if we click on this button here, we will see the shear force diagram, and we will see that we have identical results. If we click on the deflected shape and click on fit whirl, you will see that the deflected shape shows that there is a vertical displacement at point B, which is identical to the 1.5 inches that you have inserted previously. Thank you very much for being with me in this session, and hopefully I will see you in the next ones. Best wishes.